In 1968, the Central Committee of the Communist Party of the Soviet Union issued a directive that would have far-reaching implications for Soviet and later Russian tactical aviation. During the preceding decade, they had overseen the fielding of 4 new interceptor platforms, aimed at plugging the gaps in their vast northern border. But even so, and despite the cancellation of the Valkyrie, the border remained porous. In wartime, many of SAC's B-52s would be able to cross unmolested, and then they would be free to attack their targets deep within the motherland. The Soviets had built a network of radars in the Arctic, but they could only detect low-flying opponents at close range. The MiG-25 PD and the Sukhoi Su-15 Flagon lacked the range to fill in coverage gaps with standing patrols. The massive Tupolev Fiddler had the range, but it lacked the weapons system to deal with low-flying enemies. Everything else in the inventory, including the new MiG-23, was useful only for point defense. With all of this in mind, the Central Committee's directive instructed the Mikoyan and Gurevich OKB to develop an aircraft designated YE-155M. 3 versions of the platform were required: an MP Interceptor, MF frontal bomber, and an MR recon plane. The Interceptor was to have long range and a cruising speed of a casual 3,000 kilometers an hour. That's 1,864 miles an hour or Mach 2.83. Avionics were to be heavily upgraded over the already impressive Smerch radar in the MiG-25. YE-155M was to be able to destroy multiple targets ranging from bombers to cruise missiles in a single sortie. Because of the long mission duration and potentially complicated engagement geometries, 2 crew members were needed. A weapons systems officer would manage target tracking and navigation in the back. Given the relative success of the MiG-25 PD, MiG's response was based on that aircraft. Their YE-155MP, MP standing for Modified Interceptor, retained most of the same fuselage as the MiG-25, but it had different wings. Version A had trapezoidal wings with small lurxes. Version B had swing wings. Version C was a tailless delta. The tailless delta, which became known as YE-158, didn't go much beyond a sketch. The variable geometry aircraft sketches were essentially a MiG-25 crossed with a MiG-23, including a move to a single fin and rudder with the same fillet on the dorsal spine. 2 giant Solovyov D-30F6 afterburning turbofans provided the power. Large air-to-air missiles moved to fuselage recesses, with short-range weapons hung on wing pylons. In simulations, the variable geometry wing reduced takeoff length, improved rough field performance, allowed for low-speed loiter, and thus increased mission duration and gave better turning performance within visual range combat. But since none of these characteristics were particularly useful in an interceptor, MiG ultimately decided to terminate this line of development. The project therefore proceeded with a variation of the more conventional version A concept, under the internal project code 518. Since there was a lot to do, the first detailed realizations of the concept altered the wings and forward and center fuselage of the MiG-25, but they retained the tail unit. As on the variable geometry aircraft, 518 had 4 large R-33 AMOS missiles in recesses under the fuselage. A tactical bomber version of the concept was also drawn up, with side-by-side seating and heavy anti-radiational cruise missiles under the wings, but this didn't proceed beyond models. By 1972, MiG development was well underway, using an afterburning version of the large D-30 turbofan. This motor had debuted on the Tu-134 short-haul airliner in 1963. Development into the D-30F for the YE-155MP had begun in 1968 alongside airframe design, with the intention of creating an engine with about 34,000 pounds of thrust in afterburner. The motors were so large that the petals on the inboard side of the afterburners had to be removed to fit the engines close together in the airframe. A fairing fills in the gap between the 2 motors. The new engine was obviously important to give the desired combination of range and speed, But the centerpiece of the new fighter was the SBI-16 Zaslon phased array radar. Zaslon's development was entrusted to the Phasotron Radio Equipment Design Bureau at Zukovsky. They were responsible for the radar itself, the fire control system, and the seeker heads of the new R-33 missiles. Integration of the components was subcontracted to the State Research Institute for Aircraft Systems. The idea of having all weapon system electronics developed by a single organization was new in the Soviet system. Zaslon itself was rather different from Western systems of the era. It's often compared to the AWG-9 in the F-14A Tomcat, but the two aircraft's missions were quite different. The Tomcat was designed to operate alongside E-2 Hawkeyes, which would locate raids and direct interceptors to engage them. YE-155 would operate alone above the northern expanse. Zaslon, meaning barrier in Russian, thus needed to have AWACS-like capabilities as well as the ability to track and target multiple enemies at long range and on widely spaced bearings. The latter meant that a mechanically scanned system like the AWG-9 wouldn't be suitable. Although a Tomcat could track and engage up to 24 targets, it could only do so in a relatively narrow cone ahead of the aircraft. The radar scan width for the Zaslon was thus set at 200 kilometers at the radar's horizon, allowing a formation of 4 aircraft to cover 800 kilometers of border. The maximum number of simultaneous targets to be tracked was 10, although 4 R-3 missiles were all that was carried. Detection range against a target with the 200 square foot or 19 square meter radar cross-section of an SR-71 was 200 kilometers or 124 miles. Tracking range against a Badger was set at 120 kilometers, 90 kilometers against an incoming fighter, and 70 against one flying away. That's 75, 56, and 44 miles. These stretching requirements caused the Phasotron team to decide on a fixed antenna with an electronically scanned beam. Although the norm today, in 1969 this was a bold and risky decision. Its development would take until 1975, when the 4th version of the concept was flown on a Tu-104, fitted with a modified nose cone and missile pylons from a Tu-16. Even today, Zaslon is remarkably sophisticated in some ways. When it entered service, it was the only radar antenna able to operate at 2 different bands, in this case X and L, and thus it could simultaneously track targets and provide continuous wave signals to guide semi-active radar homing missiles. It's effectively 2 phased array antennas integrated into a single package, creating a 3-channel monoblock phased antenna system that allows search, target tracking, and IFF. It's a pulse Doppler set with a very high pulse repetition frequency. A digital processor provides Doppler filtering, and the overall system has pulse Doppler mode supporting look-down, shoot-down engagements, as well as detection of targets far below the aircraft's altitude. The complete 8B radar weighed 2,600 kilograms and consisted of 7 subassemblies: a transmitter, a receiver, a pulse generator, a digital processing unit, a data recorder, and an integration bus. The digital processing unit was the cutting edge of Soviet computer technology. It was a small computer called the A-15A Argon, and it could handle only 200,000 short operations a second. That made it about a third as fast as the older computer in the F-14, but it was the best that Soviet industry could manage. The radar fed signals to a weapon control system that generated the necessary commands to prepare missiles for launch. The actual launch preparations and the launch itself were carried out by a Weapons Selector Subsystem, or WSS, that included a logical automatic control module, a stores indicator panel, a missile selector panel, and a ground weapons preparation panel. The Weapons Selector Subsystem then supplies the weapon control system with information on the type, location, and quantity of weapons carried, and allowed the changing of modes of the weapons in flight. If an armed missile was selected and fired but didn't work, then the WSS would automatically select another one and fire that. Missiles were selected by the weapon systems operator by flipping the appropriate arming switches on the weapon selector panel, and they were fired by the pilot in beyond visual range mode by pushing the fire button on the control stick. There was also a switch in the forward cockpit that enabled the pilot to use the fire button for attacking targets within visual range without them being cued by the Wizzo. There was an integration bus that allowed all the different components of the system to talk to each other. It might have been slow as a computer system, but it turned out to be a reasonably reliable part of the entire aircraft. It was able to automate plotting of target trajectories, calculate interception courses, and through integration with the new lightweight ARC-19 computerized autopilot, it could also fly the plane to the right point in the sky. An APD-518 data link connected the aircraft systems to the ground-based components of the integrated S-155 interception system. That allowed up to 4 aircraft in a formation to exchange data, provided they were less than 200 kilometers apart. It could also communicate information to lesser interceptors like MiG-25 PDs and some versions of the MiG-23. Cramming all of the computers into the airframe was a challenge. Poor performance of computers in early prototypes was found to be caused by the relative location of different parts, all of which emitted electromagnetic signals that could interfere with each other. Many iterations were required to successfully locate everything. Although Zaslon was designed to be much more resilient to ECM than earlier systems, a backup infrared search and track system was fitted so that the Wizzo could find a target that had successfully broken a radar lock, and then he could cue an IR missile to attack it. There was originally meant to be an IR R-33 for this purpose, but in the end, one was never developed. The Erst is in a cylindrical housing that swings down from under the forward fuselage when in use. It's cooled by liquid nitrogen from a bottle. The original system had a range of about 120 kilometers against an SR-71 in full burner, and 40 kilometers range head-on against a tactical fighter. It had a 120-degree horizontal field of view that extended 6 degrees above and 13 degrees below the aircraft. Precise navigation was another difficult challenge for the avionics team to overcome, as well as needing to ensure accurate navigation over the large areas over which the YE-155 would roam. The peculiarities of the R-33's guidance system made an accurate INS reading critical. Because of its long range, the R-33 spent the majority of its flight on the way to a precisely calculated point in space. When it got there, the radar would be activated and the missile would acquire its target. The accuracy of the missile was thus a function of the radar seeker, its internal INS, and the INS in the launching aircraft. The designers had to engineer out as much drift as possible, as the MiG could well have travelled for hours before launching a missile. All of this was further complicated by operating close to the North Pole, where magnetic compasses can be rather unreliable. The final NK-25 navigation suite consisted of a pair of IS-172A INSs, each built around the Maneuver digital processor. These were supplemented by a Shoran set and a Tropic Loran set with an error margin of between 0.13 and 1.3 kilometers per 2,000 kilometers travelled. With so many overlapping technical challenges, it's little surprise that it took the best part of 7 years to make a system that broadly functioned as intended. So while all of that development was going on, MiG's task was to build an airframe around the large new motors and the sprawling new avionics, without deviating too far from the MiG-25. The bones of that aircraft were good. So the YE-155 and the MiG-31 were made of the same mix of materials as the Foxbat. The structure is therefore 50% steel, 33% aluminium alloys able to resist 150 degrees, 16% titanium and 1% composites. For the most part, the aircraft is spot and argon arc welded together. The overall shape is similar to the Foxbat, but by modifying the intakes, MiG were able to create a more purposeful lifting body that generated half of the aircraft's lift from the fuselage. The underside of that fuselage was extensively modified so that the large R-33s could be carried in tandem pairs, semi-recessed into the aircraft. The missiles are on pantograph launchers that swing down to place the missile into the airflow before the motor fires and the weapon flies out. The nose shape was modified to suit the new fuselage. It's made of dielectric material, and it covers the Zaslon radar's fixed 1.1 meter or 3'7" diameter antenna. Fuel is contained in 7 tanks in the upper part of the center fuselage. Each wing also has 2 integral tanks near its root, and the fins have 1 tank each in them. A total of 18,500 litres or 5,900 gallons could be carried internally, although the normal load was 13,700 litres. The pronounced dorsal spine contains the control runs and the braking parachutes. There are two of those, and they're in a cruciform shape when deployed. Hydraulic and pneumatic systems and the air conditioning system are on the fuselage sides. Cambering the wing and adding 70-degree swept lurxes delayed the onset of stalls at lower speeds for such a heavy aircraft, and they increased manoeuvrability at high angles of attack. Going from 2-spar to 3-spar construction of the wings improved their rigidity versus the Foxbat. The wings are quite large, with 663 square feet of total area and a 40-degree leading edge sweep. As I mentioned, they generate only about half of the aircraft's total lift. Each wing had 2 pylons under it. The inboard pair could carry a pair of Aphid or Archer short-range missiles on double launchers, or a single Alamo or R-40 Acrid medium-range missile. In order to carry the R-40s, one of the R-33s would be offloaded and replaced with an APP-46TD interface pod that provided mid-course guidance to the missiles. I assume the pylons had nitrogen bottles in them, as the seeker in the IR R-40TD required external cooling. The outer pylons are plumbed for 2,500-litre drop tanks, but in practice drops were very rarely carried. To improve lift when the 155 was loitering at slow speeds, 4-piece leading edge and 2-section trailing edge flaps were fitted to the wings. The front main landing gear doors double as speed brakes. The main wheel bogies on those landing gear are a bit unconventional as they don't share a common track. This was judged both easier to fold into the aircraft, and it resulted in lower ground pressure and thus better rough field potential. The horizontal tail is a slab type. The large fins have dielectric tips covering the aerials underneath. There's also a pair of ventral fins to improve lateral stability. They're canted outboard by 12 degrees. As I said earlier, for the tactical version and the Interceptor version, a side-by-side cockpit was considered for a bit, but in the end a tandem arrangement was used. The new canopy was made of a new type of heat-resistant plexiglass called SO200, able to resist up to 220 degrees, caused by prolonged high-speed flight. The canopies could be partially opened at up to 30 km an hour to assist with ventilation and visibility when taxiing. Pilots sat on K36D00 ejection seats. The front cockpit featured a large PPI-70D color head-up display, which gave useful flight and mission-related information. The control system is mechanical, with cables and push-pull rods. Controls aren't HOTAS, and because the quality of MiG-31 units was higher in the VVS, there were many controls and workload was higher than something like a MiG-29. The rear cockpit is separated from the front one by a 10mm piece of plexiglass. The console's dominated by a large circular tactical situation display, which shows the employment envelope for missile engagement. In this picture, the small area highlighted ahead of the aircraft represents the engagement zone for short-range missiles. 2 small multifunction CRTs were also fitted to the right of the main screen. The Wizzo could use the radar in 3 modes, one optimized for detecting closing targets, one for targets moving away, and a combat mode with automatic lock-on. The rear cockpit also has a telescoping control stick and sufficient flight instruments to allow the plane to be flown from the back, albeit with terrible visibility due to the massive switch panel directly ahead. A periscope was fitted to the canopy to give a forward view. 2 prototypes of the YE-155MP were constructed at the MiG experimental plant in Moscow. The Gorky factory was also given instructions to tool up for a larger pre-production batch that would follow the first 2. The first prototype, Blue 831, was completed in 1975. It lacked the radar, most of the avionics, and the internal cannon, and it was intended for validation of aerodynamics. It took its first flight on the 16th of September 1975. Blue 832 had the avionics and the radar. It flew in May 1976. Testing went reasonably well, although the radar and the engines both proved in need of refinements. The potential was there, though, and in 1977 the Gorky factory rolled out the first pre-production MiG-31. MiG-31 had numerous changes over YE-155. The wing fences, lurxes, main air brakes, and landing gear doors were all reprofiled. An improved Zaslon based on the Y155MP trials was fitted, and for the first time, so was a GSH 623 Gatling cannon. The cannon would prove to be the source of many issues, but on paper it could fire 23mm rounds at a rate of either 6 or 8,000 a minute at a muzzle velocity of 2,300 feet a second. It was mounted on the side of the starboard air intake trunk, just aft of the starboard main landing gear unit. Although it's tempting to imagine that this gun was for engaging other fighters, in reality it was a one-shot weapon for use as a last-ditch option against a bomber. Only 260 rounds were carried, enough for a second and a bit of firing. The gun also proved so unreliable in practice that its use was prohibited for much of the first 15 years of the type's service. The Solovyov engines were extensively improved as the D30F6. They gave a shade under 20,700 pounds of force dry and up to 34,620 in full afterburner. There was a degree of variability in actual output that would likely have been unacceptable in a Western fighter. Each of the mighty engines weighed just under 2.5 tons, or 5,300 pounds. Blue 11, the first of the initial batch of 2 production examples, actually lacked a radar and was used for aerodynamic, static and fatigue tests. Blue 12 had everything fitted, as did the second batch of 3 aircraft and the third batch of 4 aircraft. Even though they were supposedly improved, the D-30s proved to be dreadful engines in this early configuration. Test pilot Boris Orlov experienced an engine failure on Blue 11, but managed to get the aircraft back on one motor. When the engineers inspected the aircraft, they found that the compressor blades had escaped from the engine casing, destroying one of the hydraulic systems and various other items of equipment. Blue 11 was lost shortly afterwards when another engine had a catastrophic failure and debris ignited the fuel tanks. Both crewmen ejected and escaped the fireball. Another aircraft was nearly lost when both afterburners disintegrated during a low-level supersonic cruise. The fuel system was little better than the engines. Blue 303 from the third pre-production batch suffered a line failure that spewed fuel over the engines. The aircraft was only saved because the D-30's casing temperature was too low to ignite the fuel. The avionics proved to be more reliable. A major milestone was reached on the 15th of February 1978 when a prototype MiG-31 tracked 10 Tu-16 and IL-28 bombers flying at different altitudes over a 150-kilometre wide strip of sky. On the 28th of August, another aircraft tracked 10 target drones and then successfully engaged 4 of them with R-33s, destroying all of them. Later in the test program, 4 MiG-31s fought a simulated air battle against 10 drones attacking Volgograd on a 100-kilometre front. All drones were shot down. Engagements against low-flying drones simulating cruise missiles were similarly successful. One such test in October 1978 was witnessed by a US satellite, sparking concerns in DC about the effectiveness of their new cruise missiles. Just a month earlier, the Pentagon press secretary had assured the press that reports of Soviet aircraft shooting down the missiles were false. He was forced to issue a retraction when the photos were leaked. Despite the engine issues, which were still being worked through, full-scale production began at Gorky in 1979. The MiG-31 was, and still is, a large aircraft. It's just over 74 feet long with a span of 44 feet. Empty weight was 48,500 pounds. The wing loading at normal load of about 90,000 pounds was therefore 136 pounds per square feet. It wasn't likely to win a turning fight with anything. But that wasn't the point. With decent aerodynamics and nearly 70,000 pounds of thrust, the MiG-31 was capable of Mach 2.8, and it could climb to 67,000 feet and beyond. Patrol endurance was over 2.5 hours. Maximum range with 4 R-33s and internal fuel was 870 miles, although a supersonic intercept was only feasible at about 450 miles from base. Initial operating capability was achieved in 1980, using just a handful of aircraft. Full-scale delivery started in 1982, allowing squadrons flying the Tu-128 to convert to the new type. The first MiG-31 squadrons were in the Moscow air defense zone, the Far North and the Soviet Far East. These two commands were particularly beset by overflights and intrusions by USAF and Navy aircraft. In the Soviet and later Russian telling, the Foxhound, as NATO designated it in 1982, gave SR-71 crews something to think about, as they could no longer be sure that they could evade interceptor radars and outrun any missiles shot at them. There are even claims that Foxhounds intercepting SR-71s in international waters forced them to turn away from the border. The SR-71 crews tell a rather different story. Tooling along at Mach 3 and 75,000 feet, they would watch the MiG-31s climb towards them, able to track the Blackbirds by following their contrails. The crews were told that a combination of their low radar cross-section and the thin air made it impossible for the R-33 to get at them, so they basically ignored the Foxhounds. Because the SR-71s were often on peacetime aerial reconnaissance program sorties, the Soviets knew what course they were on and when they would appear. But even if they set up head-on, at about 65,000 feet, the MiGs would run out of airspeed, well outside the launch envelope for a missile shot, against such a fast-closing target. In any case, in the 80s, the Blackbird crews stayed in international waters. Although the MiG-31 was generally easy to fly, it did have some foibles. The main thing that pilots converting to the type had to be aware of was the high landing speed. Being heavy to start with, even a lightly loaded Foxhound landed at 177 miles an hour. Add some fuel and weapons and that drifted up to 186 and higher. Another small thing the pilot had to watch for were low-speed stalls. Although it was the first Soviet fighter to deploy with a cockpit audio warning system, the MiG-31 hadn't been intended for close-quarters maneuvering, and thus it lacked a stall warning system. Get low and slow and a pilot could be in trouble. The engines continued to be troublesome in early service too. Poor quality control meant that the turbines still had a tendency to throw their blades, causing engine fires. If a motor did fail and the fire wasn't catastrophic, then the fuel consumption of the remaining motor was drastically increased, which could spell disaster if it happened a long way from home. A lot of older hands therefore took against the Foxhound in its early days. As well as its poor reliability, they didn't much like the long missions over featureless ice and ocean. More armour plating was added around the engines in an attempt to prevent too much damage being caused by flying blades, and the turbines were eventually modified again to make them more durable. Younger pilots and the more open-minded embraced the new fighter, though. The Foxhound was a vastly more capable platform than the Flagons and Foxbats it replaced, and that meant a much greater variety of mission profiles. As initially specified, in wartime the MiG-31 was to be deployed in flights of 4, covering 800 kilometers of the horizon. Each aircraft exchanged data with the one next to it, but it might also be called upon to act as a mini AWACS. In this role, each fighter would direct up to 3 MiG-23s, MiG-25s, MiG-29s, or Su-27s. These aircraft would be free to approach their targets with their radars off, and thus would only be detected at the last moment. This capability was not developed in the West until long after the Cold War ended. Although much of the work was done in the back, the pilot was the aircraft commander and made the decisions. Alongside the commanders of the new mainstay radar pickets, MiG-31 pilots were the first airborne commanders able to direct an air battle outside of GCI control. If called upon to make its own intercept, then the crew would fall back on the Zaslon's exceptionally high degree of automation. When a contact was detected, the pilot would first ensure that all his weapons were armed and the R-33 was selected. As soon as the contact got into tracking range of about 75 miles, Zaslon would automatically select it, providing that it did not show as a friendly when interrogated by the IFF. The target's bearing would show on the HUD so that the pilot could bring the aircraft's nose to the right point and get the Pipper on target. The R-33's envelope meant that almost every closing target was immediately in range when the Pipper was on it. If it was, then the pilot simply squeezed the trigger and kept pointed at the target until it was destroyed. If there were multiple targets, then he simply squeezed the trigger for the first, then used a control on the stick to select the next, and so on. After extensive testing, the S-155 weapon system was judged to be highly lethal, even in the face of the jamming that might accompany a SAC raid. As well as ECCM, the Zaslon could put a great deal of power into the air and thus burn through the jamming put out by the self-protection systems on the B-52 and B-1B, or so the designers thought. Whether it's true is hard to establish. If the bombers were able to launch their missiles, then the Foxhounds would go after them. But with only 4 missiles per aircraft, the likelihood was that a volley of cruise missiles would overwhelm a single flight. During the cold version of the war, the MiG-31s were immediately tasked with a variety of missions. These revealed some deficiencies. Although the aircraft had decent range, early sorties to shadow NATO recon and ASW aircraft snooping around off the Kola Peninsula revealed that the Foxhound still lacked endurance when operating over 600 miles from base. Faced with cruise missiles, it would also be preferable to be able to intercept incoming bombers at or even beyond the US border. A Foxhound fitted with an in-flight refueling probe on the port side of the nose was developed, and 2 MiG-25s were modified to test it, followed by a production MiG-31. A probe and drogue system was used, limiting the fueling options to either the IL-76-based Midas or the small number of Bison tankers. Demo flights were made, including a nearly 9-hour effort, including 2 stops on the tanker and 2 simulated engagements. Normal mission duration was expected to be more like 6 or 7 hours. Development took time, though, and production MiG-31s with the system weren't built until 1990. The MiG demonstrator for the system, White 374, was finished in a natty blue scheme and was the aircraft used to demonstrate the type at international air shows as communism wound down. The other modification to the type was rather forced upon the Soviets. When Tolkachev was unmasked as a spy in 1985, it was discovered that amongst the many secrets he had passed to the US were the detailed specifications of the Foxhound's avionics and the R-33 missile system. MiG therefore launched a crash program to reassert the MiG-31's dominance. Their efforts took 2 tracks. One was the advanced MiG-31M, which took the entire concept to the next level. The other was a more modest upgrade package called MiG-31B. An uprated RP-31A or Zaslon A weapons control system was at the heart of the upgrade. This was integrated with a new R-33S missile with extended range and the option of a nuclear warhead. The avionics package also allowed signals from a ground station or a ship to be relayed to the aircraft and used to guide an automatic engagement. Navigation was further upgraded, as was the ECCM system. Built-in avionics testing was improved, and the in-flight refueling probe was now a standard fit. After a short run of non-suffix MiG-31s made in 1990, the B model replaced the original later that year. Many non-suffix aircraft were later upgraded to B standard. That was it for the Cold War Foxhounds. 341 of the original, 100 original with refueling probe and 100 B models were built, the vast majority during the Soviet era. Today's modernized BM variant is a deep upgrade of the MiG-31B. I'll talk about that and some of the specialized versions in a moment. The MiG-31 was the most advanced fighter built in the Soviet Union from an avionics perspective. Because of this, it attracts a great deal of exaggerated commentary about its capabilities, particularly in comparison to the US Navy's F-14 Tomcat. Those 2 aircraft have superficial commonality in that they're both large, 2-seat aircraft that mount powerful radars and they carry long-range air-to-air missiles. But that's basically where the similarities end. The Tomcat was designed to be used in large numbers under the coordination of E-2 Hawkeyes. It was also a fully capable air superiority fighter that could mix it with almost any tactical fighter of the era up close. As I've said already, the Foxhound is kind of a mix between a traditional Interceptor and an AWACS. In some ways it did in the early 80s what an F-35 does today, using its powerful radar and, relative to other Soviet aircraft, sophisticated avionics, to enhance the abilities of lesser aircraft. If it had ever been deployed as a traditional air superiority fighter, then its value would have been that of a Super Foxbat, using its speed and long-range weapons to hit and run. In any sort of roller, it was dead meat. I nearly got trapped into an assessment of whether the AWG-9 or the Zaslon was the better Cold War fighter radar, but in truth it's a rather pointless comparison. The 2 systems were unlikely to ever have been pitted against each other until US carriers were able to close on the motherland in the later stages of a conventional conflict. They were optimized for different purposes, and in my opinion it's sufficient to regard them both as highly capable weapon systems and leave it at that. Their relative impact on the strategic calculus is, however, worth discussing. I've said before that the F-14 Phoenix Hawkeye combination tipped the naval balance of power quite decisively in NATO's favour. Because of the relatively modest number of Soviet bombers assigned to anti-shipping operations, F-14 drastically reduced the plausibility of Soviet airstrikes being able to deter carrier groups from operating near their bastions, and thus the carriers were able to threaten Soviet nuclear forces. Foxhound also pushed out the defensive perimeter somewhat. The issue for the PVO was that the border was still large. There were a lot of bombers, and they each carried a lot of missiles. A B-52H carried at least 8 and potentially up to 20 AGM-86 cruise missiles. The B-1B could carry 8. With only 4 R-33s per aircraft, and insufficient numbers of total aircraft to allow them to concentrate in one area, the chances of leakers were reduced with the MiG-31 in service, but not decisively so. Low-rate production of the mainstay also didn't help, because the ideal situation would have been to vector larger formations of Foxhounds towards the ingress points used by SAC, rather than having to form a patrol line. That said, deployment of the Foxhound did lead to accelerated development of the stealthier AGM-129, which was first fielded in 1990. The Foxhound did therefore alter the strategic balance a little, but not as much as the Tomcat. I'm sure there'll be a good deal of irritation in some circles about that conclusion. The Foxhound remains a slightly enigmatic asset and one that gets assigned all sorts of supernatural capabilities. Development of the uprated MiG-31 I mentioned earlier began in 1985. PVO's senior commanders wanted an even more capable aircraft with better radar range, more magazine depth, and the ability to maximize the capabilities of the early MiG-31s and forthcoming Bs. They were a sort of command aircraft version. So whereas the B model had minor modifications to the Zaslon, the M did away with the original entirely and replaced it with a more powerful Zaslon M and up to 6 new R-37 air-to-air missiles. Zaslon M had a target acquisition range under ideal conditions of over 220 miles. More computer power meant that it could track 24 targets simultaneously while engaging 6. R-37 has a book range of 180 miles, although whether that was a practical reality is quite debatable. It was inertially guided, then active radar in its final phase. The R-37 was statically unstable, so it was highly maneuverable for a relatively large munition. The 6 missiles were recessed in pairs under the fuselage, and 4 R-77s could also be carried under wing. A new Erst was paired with a laser rangefinder. To make way for more avionics, the gun was deleted. The Wizzo's retractable control stick also went in the bin, as did his periscope. His cockpit was crammed with kit, including 4 multifunction displays. In general, the internals were extensively rearranged. For starters, the nose diameter had to be expanded to make space for the Zaslon M's larger 1.4 meter or 4'7" antenna. The nose was canted down 7 degrees so that the pilots could see out. Behind them, the fuselage spine was bigger to house another 300 litres of fuel. As weight grew to nearly 115,000 pounds or 52 tons, it became necessary to fit D30-6M motors and increase the size of the Lurxes. The leading edge of those Lurxes were curved now rather than straight. There were larger ESM pods on the wingtips. The aerodynamic changes give a strong impression of a team trying to figure things out as they went, and the MiG-31M is a generally rather dumpy-looking aircraft. A test batch of 6 planes was built at Gorky. The first aircraft, which was a modified MiG-31, flew as early as the 21st of December 1985. The first proper MiG-31M, tail number Blue 52, first took off on the 27th of December 1986. It was promptly crashed on a subsequent test flight. The other 5 and the hybrid aircraft flew extensively, although the hybrid was eventually scrapped for spares at Zukovsky. At one stage in the early 90s, one of the aircraft successfully engaged a drone flying 186 miles away, although the exact circumstances of the test are rather unclear. It was certainly an impressive display, but it was also unusual. The R-37 actually proved to be far too complicated for the late Soviet and early Russian aviation industry to perfect. Most of the rounds launched went off on their own volition. The Russian military-industrial complex lacked the money and the capabilities to perfect the complex combination of MiG-31M and R-37, and the program meandered. An aircraft briefly performed for crowds at Zukovsky in 1995, but the program was finally killed off in 1998 with no production aircraft built, although development of the R-37 would restart in 2006. From 1997, many of the features of the M would be used as the basis of upgrades to the MiG-31B, resulting in the MiG-31BM. The radar and weapons system wasn't quite as capable as the Zaslon M as delivered, having slightly less range and only being able to track 15 targets while engaging 6. The weapons system was now multi-role, compatible with a broad range of guided missiles. The Wizzo's cockpit had many changes, including 3 LCD multifunction displays. 50 Bs and 60 of the IFR-equipped non-suffix aircraft have been upgraded as the BM and BSM, respectively. Further upgraded versions of the type remain in service today. The upgrades give them radar and missile capabilities in line with or slightly better than the 80s era MiG-31M. All of those variants are well outside the normal scope of the channel. The MiG-31D anti-satellite missile carrier that flew for the first time in 1987 was an interesting what-if, but nothing more than that. So that leaves me needing some sort of conclusion. Because it remains in service and because it can shoot the very long-ranged R-33 and R-37 missiles and the Kinshal ballistic missile, the MiG-31 is rather hyped in some circles. That is for others to worry about, though. From a Cold War perspective, the Foxhound was the most capable pure-play interceptor deployed by any nation. But that should come as no surprise, as the MiG-25 was arguably already superior to the F-106 and the Lightning. MiG-31 added genuinely impressive radar and fire control systems, as well as extended range and superior weapons. As far as I'm aware, it was never deployed by the VVS. Whether in a war with NATO it would have been deployed to Eastern Europe is debatable. The PVO tended to keep its best aircraft back to defend the motherland. For that reason, as Foxhounds entered service, more Fox-Bats were deployed in Europe. Soviet High Command was also understandably worried about the conventional and nuclear-armed Tomahawk, which could evade defences and strike targets close to Moscow and Leningrad. The Foxhound was the only platform able to effectively counter those. If it had been deployed tactically, then on the face of it, the Zaslon and R-33 combination might well have been a conundrum for NATO air superiority crews, but small numbers and the fact that the system was compromised and doubtless featured in wartime US electronic warfare systems databases would likely have limited its effectiveness. Flanker was much better suited to the intense atmosphere of the inner German border in any case. So that's it for the Foxhound. An impressive aircraft and one of the best constructed by the Soviet Union in the Cold War, but not, I'm afraid, a wonder weapon. I hope you've enjoyed the video. Thanks for watching.